Hello everyone, my name is Ofrik Lamped and I'm happy to share with you our paper Learning Object Permanence from Video. Object permanence is the cognitive understanding that objects continue to exist without change even when they are not perceived. In developmental psychology, it was shown that different types of object permanence are learned at different ages, raising the hypothesis that it involves multiple and separate cognitive reasoning mechanisms. Here we design a network to learn object permanence from labeled videos. To teach a deep network object permanence from experience, we built on a recent synthetic dataset called Cater, illustrated in this video. We observed that localizing an object involved 4 different subtasks. The first subtask is to localize a visible target object. This corresponds to the well-studied object tracking. The second subtask is to localize an occluded target object. Object becomes transiently invisible either because the target moves behind an occluding object or because an occluding object moves in front of it. Think, for example, about a cyclist driving behind a bus. The third task is to localize a contained target object. This is a target located inside another static object. Finally, the fourth task is to localize a carried object. Here, a non-visible target is contained inside a moving object, like a man that enters a car and drives away from the scene. All these 4 tasks may occur in a single video, and we aim to localize the target in each frame. We use the Cater dataset to train and evaluate models that solve the 4 object permanence subtasks. We augmented Cater videos with the ground truth bounding boxes of all objects in every frame. These ground truth labels were used to fine-tune an object detection model. We also classified each frame into one of the 4 subtasks so we can measure the quality of predictions for each subtask separately. These classes were not visible to the model during training. We train our models by feeding them with a set of videos V1 to Vn. In each frame, we're given a ground truth bounding box of the target location, marked in blue. Our goal is to predict the bounding box of the target, marked in yellow, which is closest in terms of L1 distance to the ground truth bounding box. Importantly, we did not feed our model with information about which actions occur in the frame or which subtask the frame is associated with. A unified architecture designed for solving object permanence must consider the different reasoning abilities required by each object permanence subtask. The visible subtask requires the model to track a visible object along the video. The occluded subtask requires the model to remember the last seen location of the target, since it doesn't move during the occlusion phase. The contained and carried subtasks require the model to decide which visible object is currently covering the target, and hence should be tracked until the target becomes visible again. We developed an architecture that learns to solve these 4 tasks in one unified model. The architecture is inspired by the different reasoning abilities required by each object permanence subtask. We tried various architectures and found that it was important to include 2 distinct reasoning modules. The first module learns which objects should be tracked when the target is completely invisible. The second learns to refine the location of non-visible targets. This modular structure was especially useful for solving the carried object subtask. It uses soft attention to keep a hidden representation of which objects should be tracked at every time point, and to switch states when another object starts to carry the target object. To assess the importance of each module of OPNet, we compared it with 6 other architectures. All baseline models receive as input predictions of an object detector, so the perception module is the same. However, the models differ in how they reason about non-visible objects. The first model is a simple baseline LSTM. It simply applies a single LSTM to the sequence of bounding boxes predictions. The second model is nonlinear plus LSTM. It still applies a single LSTM, but increases the complexity of the input representation. To do that, it first applies an MLP to the sequence of predicted bounding boxes before feeding them to the LSTM. The next model is transformer plus LSTM. It now uses a much more complex input representation compared with the previous baselines. It uses a transformer to encode all bounding boxes before feeding them to the LSTM. It does so by applying self-attention between all the objects in a frame. Finally, the LSTM plus MLP model is similar to OPNet, except that instead of the second LSTM, it has an MLP. This baseline allows us to evaluate the contribution of the second LSTM of OPNet. We also experimented with two different program models. These baselines solve the reasoning task programmatically instead of being learned. The first program model is a tracker called dissected RPM. In this model, we initiate the tracker every time the target is not detected. The second program model implements a heuristic reasoner. When the target is not detected, the model switches to track the object that is located closest to the last known location of the target. To evaluate models, we use two metrics, mean intersection over union and mean average precision. In both cases, the mean is calculated over all the frames and videos in the test set. Our results show that OPNet represented by the brown line performs consistently well across all four subtasks. Moreover, when a target is occluded or contained by another object, OPNet performs significantly better than the other methods. For carried frames, the two program models marked with the blue and orange lines perform well when the intersection over union threshold is low. This means that the models provide a good coarse estimation of the target location. OPNet outperforms the program models when the intersection over union threshold exceeds 0.6, providing a fine-grained estimation of the target location. So far, we described localization of the target on each frame. In contrast, the original Cater paper introduced a snitch localization task and aimed to localize the target only in the last frame of the video. They also formulated localization as a classification problem. They divided the XY plane with a 6x6 grid, and the goal was to predict the cell that contains the target. We evaluated OPNet with the original task from Cater using the exact setup of their work. In this setup, OPNet again significantly improves over all baselines from Cater. It cuts down the classification error from 40% error down to 24%, and the L1 distance from 1.2 to 0.54. We present interesting examples of OPNet's successes and failures, adding insights into the behavioral limitations of the OPNet model. In the videos shown on this slide and the next one, the blue box marks the ground truth location of the target, and the yellow box marks the predicted location of the target. Moreover, the videos are slowed down dramatically to make it easier to follow the target. The video presented in this slide illustrates a win example. At the beginning of the video, the target object is visible. Then the target becomes covered and carried by the small red cone. Next, the big golden cone covers and carries the red cone, illustrating a recursive containment and carrying of the target. This example demonstrates the power of OPNet and its who-to-track reasoning component. OPNet succeeds to localize the target throughout the entire video, handling long phases in which the target is completely invisible. The video presented in this slide illustrates a failure example. It shows an example where OPNet fails to switch between tracked objects when the target is carried. The model accidentally switches to a wrong cone object, the yellow cone instead of the brown cone, that already contains another object, not the target. What is interesting, though, is that OPNet properly identifies when the yellow cone is picked up. It switches to track the blue ball located underneath the yellow cone. It suggests that OPNet has learned an implicit representation of object actions, like pick up, slide, contain, etc., even though it was not explicitly trained to do so. We consider the problem of localizing one target object in a highly dynamic scene, where the object can be occluded, contained, or even carried away by another object. We named this task Object Permanence, matching the cognitive concept of the same name. We presented an architecture called OPNet, whose components correspond to the natural perceptual and reasoning stages of solving the object permanence task. We believe that object permanence can play a significant role in numerous applications, including automated supermarkets, tracking concealed weapons, and shoplifting monitoring.